as a quick reminder of some things coming up, okay, the unit exam for this unit that we just started, okay, is going to be June the 9th. So make sure that you are ready for June the 9th. That is going to be the day of your unit exam. It will definitely be done by then. Okay, so just make sure you're prepared. And obviously your final exam is coming up. Okay, I know it still seems maybe like it's a little ways away, but it's going to be on top of you before you know it. So just make sure you're ready for that. And you should probably be starting your studying. Okay, so get going on that kind of stuff, getting notes organized, maybe having a look at some questions from the other units. See if you can still balance equations and you know, something like that. Okay? And then obviously come in for help. Okay? If there's something you don't understand, I'm available for help all the time because I have no life, so come and see me. Okay? And I can give you some help. We will have 4 days for final exam review. Okay, I mean, if nothing goes sideways on this, we'll have 4 days for final exam review. So that Monday, we'll do chemistry. The Tuesday, we'll do biology. The Wednesday, we'll do physics. And the Thursday, I'll just take general questions from you guys, and we can go over some examples and things like that on the Thursday. Okay, but that's my plan for that last week of classes. All right, because I know you guys have probably got, you know, other tests and things like that going on that week, so that's what we're going to do in this class. The climatogram activity is the last thing you are going to hand in to me. Okay, I will not be assigning anything. So that you're hopefully all done because you had lots of class time for it. Okay, so that's it. After that, you have your Unit 4 exam and your final exam from me, and that's it. On that note, things handed in. If you have any assignments that you have not completed that are late, I will still accept them. Okay, not for full marks obviously, but I will still accept them up until June 16th at 3:20. I will not accept anything for marking except your final exam after that day. Okay, so if you want it marked, if it's important to you, okay, it's a good way to contribute to your mark being as high as possible before the final. Okay, get it to me by 3:20 on June 16th. Okay, what I will not have is someone coming to me on June the 30th and go, oh, Mr. Coder, I failed, and now I need to hand in all the assignments I didn't do. And I'll say, and I need to go on holidays and not mark anything. Bye-bye now. Okay, I don't want that for you. So, okay, get those assignments done. Okay, they're learning activities. They don't help you when the course is over. So get them done before the final exam so that they can do what they were meant to do. All right. Questions on you guys?
How much is the final worth?
Good question. The final exam is worth 10%. Okay, that is what we have all agreed our science 10 finals will be worth. So 10% of your final grade. I adjusted the weightings of all of your grades last week, so you may have noticed your mark changed even though you didn't hand anything in. Okay, that's because I changed the weightings around to account for the fact that the final exam is no longer worth 10.
What did that like 10%?
I kind of spread it evenly throughout your quizzes, your classwork, and your unit exam, so they all went up. Okay, so key points for today. We need to understand the 3 parts of the Earth. Okay, we need to understand on how energy on Earth is absorbed, used, and reflected. Okay, instead of used, we also sometimes use the word converted. Okay, because obviously the light that comes to Earth, or the energy, sorry, that comes to Earth as light and has to be converted into other forms. Okay? And then understand how the energy and the Earth interact to produce the conditions necessary to support life. Okay? All right, so the first part of the Earth is the most important part of the Earth in terms of energy transfer. Okay? Not so much in terms of absorption, although it's important in that regard, but the atmosphere is the most responsible for transferring energy from one place to another on Earth because it is the most fluid part of the Earth. Okay, that means that it can move the most easily. Okay, that's what wind is. Okay, movement of air because it changes in temperature and pressure. Right? So you're never going to be asked about the layers of the atmosphere. So if you're like frantically writing down the names of the parts of the atmosphere, don't bother. I'm never going to ask you about the layers of the atmosphere. Okay? All I'm using this to show is that the stuff we're most concerned with happens in these first few layers. Okay? The troposphere is where we live. It's where life can be sustained. The stratosphere is the layer above that. Okay? There's only a couple of places on Earth where you can stand and be in the stratosphere. That would be K2 and Mount Everest. Okay? Those are about the only two places, and they're kind of on the fuzzy border between those two zones. That's why you can't stay there. Okay? So at the top of those two mountains is called the death zone, because you are slowly dying when you are up there, because the pressure is so low. It's not good for you. Okay? All right, so we're mostly looking at the atmosphere as just a layer of gas that surrounds and envelops the Earth, does lots of important things. Okay? It actually protects us from lots of the harmful stuff that the sun spits out. Okay? And as I said before, it is super important in terms of transferring thermal energy from one place to another on Earth. Okay? Via convection currents and wind. Okay, so the atmosphere plays a critical role in maintaining the Earth's temperature, which in turn has a profound effect on the Earth's climate. Much of the incoming solar radiation is reflected away from the Earth by particles like water, vapor, and ozone, and by the reflectivity or albedo of the Earth's surface. Okay, this term right here, super important. Okay, albedo comes up over and over and over again in this unit. Okay, albedo is the reflectivity of the Earth's surface. Okay. Why is the sky blue?
Because the way oxygen and light is reflected.
Okay, I would use scattered in place of reflected, but yes, absolutely. Okay, because I often get that people tell me it's because it reflects off the ocean. Okay, and I know that somewhere along the way some well-meaning science teacher told you that, but it's totally wrong. Because the ocean's not blue. The ocean looks blue because it reflects the sky. It's actually the other way around. Okay, the ocean is clear. You know, like water. It's clear. So the ocean is actually clear. It does not reflect. Light doesn't reflect off the ocean to make the sky blue. The sky scatters blue wavelengths of light under normal conditions. Okay, is the sky always blue?
Isn't it during a tornado?
If you're going to get a really bad hailstorm, the clouds will be green, yes. But I mean, like, does the color of the sky, if it wasn't cloudy, does the color of the sky change? Yes, it does. At sunrise, it's a little on the orange side, same at sunset. Or if we got a lot of forest fires going on, it can be orange during the middle of the day, or even kind of brown, okay? The reason for that is you get more particulate in the air. Same reason for sunrise and sunset. Okay? The sky appears a different color because the light is going through air that has more particulates in it. At sunset, it's closer to the ground, so it's going through air that's closer to the ground that has more particulates, and that scatters orange and red, okay, as opposed to blue. If there's really bad forest fires, you've got lots of particulate in the air, the sky can appear orange, even though it's a kind of sunny day. Does that make sense, everybody? Okay. So the amount of stuff that gets scattered is important. Okay? If we have a lot of cloud cover or a lot of pollution in the air, things like that, it changes the amount of light that actually makes it to the surface. Okay? If there's a volcanic eruption and there's lots of volcanic ash in the atmosphere, it can actually lower the Earth's global temperature several degrees. All right, so that's what happens in the atmosphere. We've got lots of backscattering that makes the sky blue. We've got absorption happening. Okay, that means that some of the atmosphere actually absorbs solar radiation, which causes it to get warmer, heated up. Okay, anytime you absorb thermal energy, you get warmer. Okay, there's a lot of reflection off the Earth's surface. Okay, some of that reflection just goes right back out into space, and some of it bounces around inside the atmosphere because of the greenhouse effect. Okay, now the greenhouse effect gets a really bad rap. Okay, it's not all bad. Without the greenhouse effect, Earth would be a frozen ball. Now, greenhouse effect getting worse, not good, because then the Earth will get too hot. Okay, but having a greenhouse effect is important for actually supporting life on Earth. Okay, look at a place like Mars, it has no greenhouse effect because its atmosphere is 1% as thick as ours, and it's cold and sterile. Okay, now you go the other way to Venus, where the atmosphere is 100 times thicker than ours, and you've got big problems. Okay, and you've got a runaway greenhouse effect that makes the surface of the planet hotter than your oven on the self-cleaning cycle. Okay, so it's super hot. Now, this thing about albedo, okay? Albedo is the reflectivity of your surface, and it determines how much energy gets absorbed and how much gets reflected and how much gets converted. Those are the three fates of light, and I want you to add that in here. Okay, the three fates of solar energy are absorption, reflection, and conversion. That has to do with photosynthesis, okay? The only organisms on Earth directly capable of converting solar energy into other forms of energy are plants via the process of photosynthesis. So those are the three things that can happen to light when it strikes the Earth's surface. It can be absorbed, and if it is, the temperature will go up. It can be reflected. If it's reflected, there's no change in energy because the energy just bounces off. And if it's converted, the energy will go from being light to being chemical energy in the form of sugars and other things that would be part of the plants. Okay? It's this process here, the conversion, that gets all food chains and all life on Earth started. Okay? Without that, it would be very different. Okay, so how does albedo affect these three things? Okay, well, albedo tells us how reflective the Earth's surface is. The higher the albedo, the more reflective the Earth's surface is. So in the wintertime, when up here at least, where the ground would be covered in snow, the albedo would be very high. And much of the incoming solar radiation bounces off. And so there's no warming effect because it just reflects back into space. Okay? So in the wintertime, okay, surface covered with snow, we get 85 to 90% of the incoming solar radiation that strikes the Earth's surface simply reflects away. Okay? Only 10 to 15% gets absorbed, and that would be areas where something is sticking out through the snow, so maybe some trees or bare rocks or something like that. Okay? Or where maybe some dust has settled on top of the snow and it's a little bit darker in color. Okay? In fact, speaking of which, that's why we put sand on the roads when it snows. Okay? I mean, people are like, well, it makes traction better. Well, it kind of does, but it does it by making the snow melt faster. Okay? We put sand and salt on the roads because the sand makes the snow darker, so it absorbs incoming radiation and melts faster, and salt lowers the melting point of water so that it can melt at a lower temperature. Okay? So those two things, that's the reason why we do those. Okay? There's an additional nice effect of having a little extra traction by having lots of little rocks on the road. Okay? But the big thing is that it lowers the albedo to a point where more solar energy will be absorbed and the ice and snow will melt faster. Okay? This is actually a big worry right now because with all the forest fires we've been having, a lot of ash has deposited out on top of the glaciers in the mountains, which has lowered their albedo and is causing them to melt faster. Okay? Because before they were gleaming, pristine white. Okay? But when that ash landed on them, it darkened it. It darkened the ice and snow, and it started melting faster. Okay? So things like that are a concern. Okay, in the summertime, when there's no snow and the plants are green, that nice color we see for 3 months of the year, okay, they're open, they're doing their photosynthesis, our rate or our albedo is so much lower that 70% of the incoming radiation is now absorbed.
almost a flip-flop. Okay, 20% gets reflected off of light-colored surfaces, and 10% would be reflected off of water bodies. Okay, large lakes and things like that. Okay, so we get a lot more energy in the summer, okay, obviously because we're tilted towards the sun, but also because our albedo is so much lower. Okay, now, here's how I'm going to ask a question like this on a test. Okay, I will have a picture, a satellite picture, most likely, okay, of a place that I pick. And I just ask you, looking at this picture, tell me what will happen to light that strikes this area. Okay, so if I show you a polar desert, okay, you would probably tell me, oh, well, it's really light in color, so the albedo is really high, very little light will be absorbed, much of it will be reflected, and there are no plants visible, so nothing will be converted by photosynthesis. Okay, conversely, if I showed you a picture of Okotoks right now as the picture, okay, you could say, well, the albedo is very low because there's no snow, so lots of energy will be absorbed. Plants are alive, it's green, so a lot of photosynthesis is going to occur, and very little reflection will occur, except possibly off the roofs of houses or something like that. Okay? Everybody got me there? All right, that's exactly how I will ask it, okay? I'm asking about the three fates of light: absorption, reflection, and conversion. Okay? Now, if you're kind of unsure about this whole albedo thing, okay, now that it's getting sunnier and hotter outside, if you have a dark colored car, okay, does it get really hot in the sun? Or if you have a light colored car? It gets a lot less hot. Yeah, if you have a light colored interior, okay, and a light colored paint job, okay, your car will not be nearly as hot when you get in it on a sunny day. If you have a dark interior and a dark colored car, you'd hardly be able to put your hand on it on a hot sunny day. All right, making sense? Okay, so that's albedo and the three fates of light. Super important. Always ask about it. All right, so within the atmosphere, there's lots of different gases, okay? Obviously, the main gas is nitrogen, but it's fairly like inactive in terms of what we use it for. But obviously, carbon dioxide is a gas that we would be concerned with. Plants need it in order to carry out photosynthesis, but it's also a greenhouse gas. So is water vapor, okay? So is methane, okay, which comes from farts, okay, and other types of methanogens, bacteria that make it, okay? You'd have ozone, which is important for blocking incoming ultraviolet radiation, CFCs, chlorinated fluorocarbons, and other things that would be in the atmosphere. Okay? And they all contribute to the greenhouse effect. Okay? They all help to trap some of the sun's solar energy from just bouncing off the Earth's surface and back out into space. Okay, the hydrosphere. So we talked about the atmosphere, it's all the gases, okay, albedo, the three fates of light. Now we're going to talk about the hydrosphere, which is all the water on Earth. Where is most of the water on Earth? In the oceans, okay? Where is most of the fresh water? Well, some of it's in lakes, but where is the bulk of it? Some of it's underground too. But there's even more of it in this other place. Okay, there's some of it there too. Still not the place I'm thinking of. Got any guesses? Glaciers. Much of the world's fresh water supply is frozen, okay, in ice caps and glaciers. Okay? We are very fortunate here in Canada. We have one of the largest freshwater resources available in the world because of all the glaciers that we have. Okay, so we have lots and lots of nice fresh water, especially here in Alberta where we're so close to the source. Okay, so all the water on, above, or under the Earth's surface is known as the hydrosphere. It can be water vapor, liquid water, and ice. And less than 1% of all the water evaporated from the surface of the Earth is returned to the same place. Okay, so if it evaporates here, it gets carried away, it goes somewhere else. Okay, if we get a big thunderstorm, it's not like all that rain evaporated from the surface right here. Okay, it probably came from somewhere else. Okay. All right, so the hydrosphere is part of energy transfers because of the water cycle.
Okay, because again, the whole theme of this unit is energy. That's why we just talked about albedo and absorption and all that kind of stuff. Well, the water cycle, which is part of the hydrosphere, also represents a huge part of the energy transfers that go on Earth. Okay? So, does it take energy to evaporate water from a liquid to a gas? It does. In fact, it takes a great deal of energy to evaporate water from a liquid to a gas. So, in this part, or these parts of the water cycle, these are energy inputs. Okay? The solar energy is coming in and it is evaporating water and turning it into a gas. So, water vapor carries energy. Okay? It's actually storing energy that was evaporated probably near the equator and over an ocean. Okay? And it can be transported somewhere else by wind. We call this latent heat. Okay? The water cycle is the only way that latent heat, which represents huge amounts of energy, can be transferred from more equatorial areas to more northerly areas. Okay, so we have water evaporating from someplace, and when it's coming to us in a vapor form, it's bringing a lot of latent heat. When it condenses, it releases that energy. Okay, so in the water cycle, these two processes, evaporation, evapotranspiration, and evaporation, and then precipitation, okay, represent the ability to move large amounts of latent heat, or transfer energy from one place to another on Earth. Okay? Huge amounts of energy are transferred that way. So when we get a rainstorm, even though it might feel a little cooler on the day when we get rain, we're actually getting energy from other places, in addition to the precipitation, because that water vapor will carry energy with it. How many people have heard this before? Watch out, because steam will burn you worse than water. Okay, why? If I have steam at 100 degrees and water at 100 degrees, the steam will burn me way worse than the water will, even though they're the same temperature. The steam has more energy because it's had to absorb energy to convert from liquid to gas. Okay? And it's a huge amount of energy. For every milliliter of water that turns into steam, that milliliter of water, that 1 gram of steam, will hold 2,260 joules of energy. Okay? That's why steam can burn you so much worse than water. They might be the same temperature, but because steam is a gas, it is holding this much more energy per gram than the liquid. Okay? That's why a big, warm, moist air mass that comes from somewhere else can bring so much energy with it, because every gram of water in that cloud has this much energy to bring. So when it condenses back into a liquid form, that energy gets released into the new area. Okay? And it's huge amounts of energy. That's why we don't get hurricanes up here. We can't build enough energy to get a hurricane to go. Okay? Because hurricanes are the result of a lot of water being evaporated and forming a big giant storm. There simply isn't enough energy or water here to make that happen. But you also don't see hurricanes forming off the coast of Newfoundland or off the coast of Vancouver. Okay? It's not warm enough. They form down by the equator and then they move northwards. And as they move northwards, they peter out. Thankfully. I wouldn't want to live in Florida. Okay? I mean, they get like several hurricanes a year, same with anywhere in the Caribbean. Okay? So that's where hurricanes are born. Okay? So. All right, does that sort of make sense? So, yes, I'm making you go over the water cycle one more time. You've only been beaten over the head with it about a dozen times already in your school career. But in this case, it's not so much about knowing the parts. You already know the parts. But knowing where energy is
in those parts. So in evapotranspiration, which is water evaporating from plants as they carry out photosynthesis, or just straight evaporation of liquid water, that is putting latent heat into the system. That latent heat can go somewhere else and be released when it precipitates out. Okay, so really important that we understand that is the role of the hydrosphere. Okay, so most of the Earth's water is obviously not fresh. 97% of it is salty, okay? And only a small portion, less than 3%, is fresh. Okay, 3/4 of all fresh water is in the polar ice caps and glaciers. Okay, that means that, like, basically the most important resource on Earth, okay, is only, what, 1/4 of the available fresh water. Okay, the rest of it is frozen.
So it is possible to filter salt water to standard fresh water, correct?
You can distill it, or you can run it through a reverse osmosis process.
So that number could change.
No, we can make it drinkable. I'm not saying it becomes part of the freshwater supply. I'm talking like natural freshwater supply. Could it become drinking water? Yes. But the amount of water that we actually drink is very small compared to the amount that's actually out there fresh. Yeah. Yes, we can make seawater drinkable. It is not an efficient process, and it wastes a lot of water. Okay? The process of reverse osmosis, for every liter of drinkable water you get, 3 are wasted. Okay? So it's actually not a very water-saving process. It can certainly clean water, but it also wastes a lot. I mean, if it's just seawater, it just goes back in the ocean. But people do reverse osmosis to fresh water as well, and it actually produces a lot of waste. It wastes a lot of fresh water. Okay, and then obviously there's groundwater. Okay, so these are the places where we would obviously see a lot of the stuff in the hydrosphere. The oceans still play the biggest role in terms of energy, okay, for the global system. Okay, now this is obviously a glacier. Okay, this is the Robson Glacier. Now, what's happening to our glaciers right now? Like over the last, 500 to 1,000 years.
It's like melting and sinking.
Yeah, they're shrinking. Okay? They're getting smaller and smaller. Now, part of that is that the Earth is in a natural warming cycle, and part of it is we're contributing to it for sure. Okay? The Robson Glacier is one of the ones that's being watched because it's receding very quickly. Okay? Now, that picture was taken before you were born. Okay? When I hiked this trail, there was a sign on the trail that said, "The Alpine Club of Canada marked this point as the toe of the Robson Glacier in 1901. We walked 2.5 kilometers before we got to the actual glacier. And that was in 2003. That's 19 years ago. Okay? Now, it's not just about it shrinking in one dimension, it's also getting smaller vertically. This glacier used to fill this whole valley. So we're talking about a lot of water being released from those glaciers. Okay? They're getting smaller and smaller all the time. And the smaller they get, the more the albedo around them goes up. And then that causes them to melt even faster. Okay? So the process kind of gains traction as it goes. Okay. All right, the third part is the lithosphere. The lithosphere is the rocky part of the Earth. Okay, the part of the Earth that is where soil and plants and things like that are going to grow, obviously. Okay, so all the rock on Earth, no matter how small, is known as the lithosphere. Okay, it's where living organisms, okay, can be present. They can also obviously be present in the ocean. Okay, but this is where, like, the stuff that affects us and where a lot of the albedo is going to be located. Okay, because the ocean's albedo is pretty uniform, okay, in most places in the world. Okay, so the importance of the lithosphere is about the soil. Okay, soil is different everywhere you go. Soil here is kind of sandy. Okay, if you go further north to like Edmonton, the soil is a lot blacker. Okay, and it feels different. It's not as gritty. It's fine. Okay, as opposed to coarse down here. Okay, and that's because down here the soil comes from sandstone, whereas up there it comes from limestone. So it's different, right? So we get different types of soil. Okay, but the soil is an ecosystem that has both biotic, that's living parts, and abiotic, non-living parts. Okay? Would you consider the stuff in that picture to be soil? It is. It's not like soil here. It's not dirt, okay? But it's still soil. It's the top layer. Stuff grows in it, but it's mostly rocks and sand. Okay? It's not great soil, but anything is soil. Okay? Now, soil in general is broken up into horizons. All I'm going to ask you about soil horizons is basically the names of them and what's in each part. Okay? So, in your soil horizons, you have the A horizon, which is made of organic materials. Okay, but we generally call it the topsoil. Okay, so if you've ever dug a hole, okay, that's the blacker part, the darker part, where you'll find like roots and things like that. Below that is the subsoil. This is mostly clay. Again, if you've ever dug a hole, you know you eventually hit clay. Okay? And that's because clay is made of much finer particles. So they can wash down between in the spaces in between the larger topsoil particles, which tend to be like sandier and bigger. Okay, so clay tends to collect underneath that. Okay, it's why if you had a sandbox as a kid and you dug down, there's always like clay at the bottom of the sandbox. Your parents did not put clay in the sandbox. It just naturally forms because dust settles and it gets washed through the sand particles and ends up underneath and makes clay. Okay. All right, and then below the subsoil, the B horizon, is the C horizon, which is our, what we call parent material, the rocks, it's the bedrock. In Okotoks, you don't have to dig very far, and you will hit this. Okay, Okotoks is built on a sandstone outcropping. Okay? In some places, it is very close to the surface. Okay? When I built not my last house, but the house before that, the house was built on the rock. I felt like that guy in the Bible who was the smart guy, okay, who built his house upon the rock. They were pulling rocks the size of Volkswagens out of the hole, okay, that they dug for my house. I was built right down onto the bedrock, which seemed really cool until I tried to build a fence. And I could dig my fence posts down that far. Then I hit the bedrock and I couldn't go any further. Okay? So in some places it's thicker than others. Okay? In some places it's really, really thin. If you go to the mountains, the soil is super thin. Okay? Because it's very young. If you go further east, it'll be thicker and thicker because it's much older. All right, so A horizon is the one we're most concerned with, or that's the topsoil. It's the layer in which the plants are growing. You can get roots down into the B horizon if it's a big tree or something with a taproot, okay? But for the most part, the A horizon is the active part of the soil. Okay, here our A horizon is fairly thick because this is grasslands, and every year the grass dies and new grass grows from it. So there's always a layer of thatch that builds up. Okay, the B horizon is the clayish part of the soil that's underneath. Okay, in lots of places the B horizon goes right to the surface. There's almost no A horizon. Like in places like the tropical rainforest where it's flooding all the time, the topsoil washes away very, very easily. And so what's left is a clayish surface. Okay. And then there's the C horizon, which as we said is mostly rock. So this would be a typical soil profile for our area. Okay, you'd have an A horizon that looks kind of like this. Your B horizon would be kind of like that. So this would be A, this would be B, and then there's your bedrock and parent material. Okay. Everybody okay with that? So all I'm going to ask is like a multiple choice question. What's in the A horizon? What's in the B horizon? That kind of thing. So it's just memorization. All right, so we already talked about this, but the Earth's a system, energy comes in, and what are the three fates?
Absorption, reflection,
Conversion. And what affects how much of each happens? Starts with A. Albedo, right? So reflectivity of the Earth's surface. Okay, how much of it gets absorbed, reflected, and converted has to do with albedo. All right, so let's get that part. Okay, so within the atmosphere, we already said the atmosphere is the most important part. It's where the bulk of the transfers occur. Okay, the three ways that energy can transfer are, and you've probably heard of these terms, conduction, that would be this, okay, convection, which would be this, this, okay? And radiation. Okay, those are the three methods of heat transfer. You probably want to write those down. They're super important. Okay, conduction, convection, and radiation. Convection is the most important energy transfer method on Earth. It's wind and things like that that move the atmosphere around. That's convection. Radiation is how it gets here. Okay? Energy gets to us from the sun as radiation. Visible light, heat, ultraviolet, X-rays, gamma rays, all of that is radiation. Okay? So that's energy that moves by waves. Okay? Conduction is energy transfer by particle collision, and it happens in solids, just solids. Okay? Convection can happen in liquids and gases. Radiation can happen in a vacuum, okay? Or through liquids and gases. Doesn't happen very well through solids. Okay? So in conduction, okay, conduction is what happens if you are stirring something with a metal spoon. Okay, like you're making soup or something like that. If you're using a metal spoon, are you eventually going to feel that in the spoon? Okay, even if the end you're holding never gets in the water, it's still going to get hot. Okay, that's conduction. At the bottom of the spoon, this bottom of the spoon is getting heated up, and the particles that make up the spoon start moving really, really fast, and they start running into each other. Okay, when they run into each other, they're transferring energy. That transfer works all the way up the handle of the spoon until it's hot enough to reach your fingers. Okay? Convection is dependent on the material, but generally slow and doesn't work over large distances. It works enough to burn your fingers if you're stirring with a metal spoon, but beyond that, it's not going to be transferring energy from Canmore to Okotoks through the Earth's crust. Okay? That's not going to happen. Convection doesn't work like that. Or sorry, conduction, sorry, doesn't work like that. Okay? Convection is something we use all the time. Okay? It's currents, convection currents, that are transferring thermal energy. Okay? We use it in our houses for heating. Okay? How many people have a forced air furnace? Okay? That's the kind that have the grates in the floor and the hot air comes out of it. Okay? That's what most of us have. You might have hot water heating in some places, okay? But generally you're going to have like a forced air furnace. Okay? And so what's happening is the furnace heats up the air and then the hot air rises. That's why we put the grates in the floor. It makes the most sense. The coldest air is near the floor. Hot air is going to go past it first, okay, and it's going to create a convection current. It's also why in the summertime, like last summer, if you lived on the second floor of your house, that was the hot part, okay? You went and hid in the basement while it was minus 40. Or sorry, plus 40.
How come in the basement they put them on the ceiling?
Because your basement is made of concrete and you can't run the pipes through the concrete. Yeah, would make way more sense and would be more efficient to put them in the floor, but it's concrete, so unless you're gonna build up a subfloor where you can run the pipes underneath, and some people do that, you can't run them through the concrete, so that's why. That's a good question. So it doesn't work, that's why your basement's generally colder, right? The hot air is already where it's gonna sit, near the ceiling, and so it doesn't work very well. It works great if the air conditioning is running, then you just lay on the floor in the basement and feel nice. But yeah, it's not going to work so well there. Okay, and so air conditioning doesn't work all that well with a forced air furnace style of home, and that's what we have here because obviously it's winter 9 months of the year and summer for 2 weeks. Okay, so we only get, when we're running our air conditioners, we're forcing cold air to go away. It doesn't want to go. Okay, so it's not as efficient to do that. Okay, so convection works like that. If you have a convection oven, same idea. There's a fan in there that keeps the air circulating and keeps the oven at a uniform temperature. Otherwise, the top of the oven would be hotter than the bottom. Okay? So lots of cookbooks say, cook this on the top rack, cook this on the bottom rack. And I'm like, my oven's convection. I can cook it on whatever rack I want. Okay? They're all going to be the same temperature. Okay, is that making some sense? So convection is really important. Lots of heat can be lost by convection. In fact, the design of our houses is a way to prevent it. So within your wall, what's inside the walls of your house? Oh yeah, okay, wiring, all that kind of stuff. What do we jam in there? Insulation. What's the insulation made out of? It's usually one of two materials. It looks like pink candy.
Definitely.
It's fiberglass, yeah,
Oh,
plexiglass is, yeah, like the bulletproof stuff, but, yeah, fiberglass, it's the pink, and then all it is like little tiny, like hair-like fibers of glass, okay? Now, the reason that that's really insulative is that glass doesn't transfer heat by conduction very well at all, so if you have fiberglass jammed in here, heat's not gonna conduct through it by particle collision, but also, because insulation, fiberglass insulation, essentially creates trapped air. Okay? When you fill your wall with fiberglass, between the fibers is air that can't move. It's trapped. So it can't move and make a convection current. If I have an uninsulated wall, okay, so this is the inside of my house, this is outside, okay? The energy is naturally going to flow from hot to cold, but it's going to do this. The air that's inside the wall is going to be warmed by the air inside my house, and it's going to go up. Well, cold air from the other side of the wall will move in to replace it. And I'll start getting a convection current forming inside my wall that's going to keep pumping the heat that's in my house straight outside. Okay? It's why your windows of your house are the least energy efficient part of it, because they're not insulated. Okay? Unless you get like triple pane and then you got stuff in between that prevents that. Okay? If I don't have an insulated wall, this is what's going to happen. Here, the air is trapped. It can't move. So a convection current can't form, and we lose way less heat through the walls that way. Okay? It's also why a quinsy or an igloo can keep you warm. When snow falls, the little flakes interlock, and trapped between them is air. Snow is an excellent insulator. Okay? Back when I taught in Saskatchewan, we actually had a whole unit on snow ecology. And on the coldest day of the year, I would take my students outside, and I would make them make piles of snow and then hollow them out to make a quinsy, which is an emergency snow shelter. Boy, you wouldn't believe how fast people can make a pile of snow and hollow it out when it's minus 40 outside. Okay? They would get inside, and they could get the snow inside start melting, just from their body heat. Okay? It insulated so well, minus 40 outside, and it can be like +2 inside the quinsy. Okay? Just because snow is such a good insulator. And on top of that, what color is the snow? It's white. So you're preventing convection, but you're also reflecting the radiant heat from your body back to you because of the light color of the snow. Okay? And the other part of this is conduction can't occur either, because conduction only occurs through solids. If you've got gaps of air, the heat can't conduct through the fluid. Okay? So our methods of insulating make a lot of sense in terms of conduction, convection, and radiation. We'll talk more about that tomorrow because it's something we apply through the unit. Okay?